All right, ladies and gentlemen, hello and welcome back once again to the longest running show in the world about data. It's called DM Radio. Yours truly, Eric Kavanagh here, folks. And I am so excited to have two of my favorite people in the world on the show today, David Flynn of Hammerspace and Mark Madsen of Third Nature. These gents know a tremendous amount about what's happening in the world of data, and that, of course, is AI. We're going to talk about a number of different things today, including these recent benchmark results by Hammerspace, the IO 500. It's a very well-known benchmark, and Hammerspace has done some amazing things there. But I first wanted to frame the discussion in my understanding of what the folks here have done. And David Flynn and his last company did some very interesting work. A company called Fusion IO. It's a solid state disk company, and they worked on the NVMe standard. NVMe is now overtaking the industry and basically opening the floodgates to allow flash memory to do amazing things. Well, flash, as you recall, was on the mind of a guy named Hasso Plattner years ago, one of the founders of SAP. And I'm old enough to remember and had been in the business long enough when he announced his plans for S4 HANA, which was going to be all focused on memory on solid state drives. Well, at the time, that seemed crazy, but he did the math and he said there's going to be a point in the future when solid state drives are going to cross over in terms of cost with spinning disk. And of course, solid state is just lightning faster than spinning disk. So he had the vision to do that, and they set out and they built S4 HANA, which is all in memory. Now, my other joke is that he did not foresee Kubernetes, and that kind of threw a little bit of a wrench in the works for his plans. But David is one of the other guys who really understands that. And the cool thing about folks who come from the hardware world is you have to understand the material science. You have to understand all the components of a motherboard, of a computer, how things work, networking, protocols, all these different things have to be really native in your mind and in your company to build stuff that really works. And of course, that's what they did. So one of the things that Hammerspace did that just blew my mind when I first learned about this company is they took something from the HPC world, high performance computing, and brought it into the enterprise data world. I'd never seen that. And I had wondered, I'd gone to HPC conferences looking around for all the enterprise folks, and they weren't there. Now, my theory is that in the HPC world, it's largely driven by universities and research centers, and they're their own center of gravity. So they are tangential, if you will, to enterprise data folks. But nonetheless, there's all this innovation happening, and the folks at Hammerspace did that. And the other thing that blew my mind is that David and his team said, you know what? We're going to go ahead and spend years digging in to clear out the cobwebs in Linux and open that to everyone so you can have standards-based functionality in the Linux kernel that allows anyone to benefit. This is very powerful stuff because here at Fusion IO, they had proprietary technology innovations, which they then opened up to the world as standards-based innovations, which is just awesome. And there are other things they're working on too, like the Open Flash platform. We'll talk about that probably on some future show and some other cool things. But David Flynn, with that background, let me bring you in. Congratulations on the results, by the way, and
Thank
maybe
you.
explain to the audience here why that's such a big deal.
So it's a really big deal because AI is not HPC, and the one big difference is that AI is mainstream. Uh, it's we don't have time for bespoke systems. We don't have time for science projects. HPC was all about science, and so you had people that could run science projects and build data platforms that were bespoke for that. What we need with AI is something that everybody and their grandma knows how to run. And frankly, that's NFS. But NFS was stuck in yesteryear because there wasn't a reason to give it that kind of crazy performance because enterprise didn't need it. And HPC was still a niche. So there wasn't really a big commercial demand for folks to fix it. Well, because of my work with Fusion IO and introducing what became NVMe, I realized at some point we were going to need file systems that could deliver that kind of crazy performance without diminishing it. And I figured at some point something would come along with that could use that. Nature abhors a vacuum, right? And if you have a potential, something's going to come along and use it. I had no idea that it was going to be AI, but I started on this project 12 years ago. And, frankly, I was surprised it took a further 8 years for something to come along that actually could really benefit from crazy high performance data feeds, massive amounts of data. But lo and behold, that's AI. And the thing about it is, it also fulfills the second thing that not only would you have the need for it, but because it's mainstream, people wouldn't have the time for bespoke systems. They would need it to be native and built in. So what I did is I went and recruited the Linux kernel author and maintainer of the network file system client stack. And I said, can we fix this? And basically what we did was we took HPC parallel file system architecture and brought it into the world of NAS and NFS. And fundamentally, that architecture is very different. Traditional NAS, traditional storage protocols are very simple. They're point to point. A client connects to a server, which means if you want to scale, you have to go through that server to get to everything else. It's like being stuck in a two-dimensional space, right? And you have to go through an intersection to get to multiple destinations. Well, what parallel file systems do that's so powerful is they move that to a three-dimensional relationship. The client connects to a control plane, and the control plane gives out routing information to go to not just one storage node, but many. In other words, it moves the whole process from having to be proxied through an intermediary to being able to be routed through a control plane. It's like having an air traffic control tower and being able to fly directly to different destinations. Now, in the bespoke world of these HPC file systems, they've used that architecture for years, but those things were bolt-ons and you had to have, a PhD to go and run them, right? But now we need AI and everybody needs to be able to do it turnkey. And so it's really important that it's standards-based and that it's built into Linux. And so these IO 500 results are so phenomenal because what they're showing is that you now have built in NFS capable of not just hanging with the big boys with these exotic HPC file systems, but we can talk about it here in a bit about how now that it is native, we can take further steps because it's part of the kernel to make things even higher performance. So that's the general concept is, Linux took over the HPC world 2 decades ago because it became too difficult to have all of these custom different operating systems.
Right.
So now, even the most exotic architecture supercomputer is running Linux as the base OS because nobody has time to relearn this stuff or rebuild it. But the data planes have been that way with Lustre and Weka and these kinds of exotic things you got to learn how to use and install them separately. What we're seeing now is thanks to AI bringing high performance data to a mainstream need, we're having to follow suit. And Linux is getting its stuff together to be able to deliver those kind of crazy performance. And I would say this is the year that parallel NFS, parallel file system based NAS is actually, a fait accompli. Not
Yeah.
just Hammerspace, but other vendors have started talking about it. Everybody's going to have to follow suit. The same way they had to follow suit with NVMe, with what Fusion IO did.
Yeah, and that's the power of standards, and that's the power of open source. I remember when Linux was
Mm-hmm.
taking off. I remember researching back in 2005, in fact, when I was at the Data Warehousing Institute, and right at that point, the Apache web server had just passed the Microsoft web server as the #1 web server, and I was
Mm-hmm.
like, well, that's pretty interesting. And I sat there and I thought to myself, and this is back in the days of service-oriented architecture for the old timers out there, and I thought to myself, this open source concept fused with service-oriented architecture is a real game changer because it's threatening the big monolithic vendors like the Oracles and the IBMs and all these guys. And of course, IBM put a ton of money into Linux, about $1 billion, as I recall. And there's a report that came out years ago that said they made that money back in like 1 year because of the innovation that kind of flooded the market. But maybe Mark Madsen, I'll bring you back in to comment on this. I mean, you're like me, you've been tracking this stuff for a long time. Standards lead to greater things. A rising tide lifts all boats. So if you can improve the foundation, which is the operating system, then everyone else can do cool things and you get a whole wave of innovation. But what do you think, Mark?
Yeah, it's this is kind of an interesting development trying to push things into Linux itself. What I'm curious about is you mentioned earlier bespoke, file systems, but isn't POSIX a standard for file systems? So, so when we're talking about POSIX file systems versus
Mm.
NFS, if you do that, could you talk a little
So
bit about the
yeah,
difference here?
you
Because
bet.
that to me is kind of meaningful because local remote file system
Yeah, yeah,
access
yeah.
is also built into the kernel there.
So POSIX is the way applications talk to the underlying file system, the open,
Yeah.
close, read, write, all that kind of stuff. And that absolutely has to be standardized. But this is taking it a step further as to how you set up and administer a network shared file system. And that's
Mhm.
what NFS, with how you do the mount, that's not POSIX, right? That goes beyond that to how you administer a network shared file environment. And with these bespoke um, uh, drag racer HPC file systems, all of that was custom. How you set it up, how you run it. It required that you put custom Linux kernel modules. You had to taint your kernel. You had to plug in stuff that wasn't. Oh, and you want to hear the biggest indictment on this? Luster, Luster was built by the DOE labs. It's open source, and yet it has never been adopted into the Linux kernel and never will be. And there are two reasons for that. Number one, it's non-standard, and the kernel guys only put stuff in there that actually adheres to a standard so that you can, keep it consolidated. And that's one of the, goes to the second reason is that Lustre, by being non-standard, is highly fractured. There's different versions, different changes here and there. And at the end of the day, it's actually rather crappy code and wouldn't meet the level of quality that the Linux kernel guys demand. And so therefore it's never been adopted in, and it won't be. So, in other words, Lustre will become part of the Linux kernel once it's actually built into NFS and that architecture. And that really is kind of what parallel NFS is. It's that architecture from the Lustre and the HPC world, but rewritten to be very precisely standardized and built into the protocol and written in open source. So yeah, you're right. POSIX is part of it. That's how applications talk to file systems. But
Right.
the how are file systems administered, the mount, the tooling, and what every sysadmin knows how to do. Every sysadmin knows how to use NAS and how to work with NFS, and that's the beauty.
Right. Yeah. So ease of adoption. Yeah. The question I was thinking about, on the bespoke was just how, like you mentioned, Weka and, one or two others. And what I remember of those is that you actually had to have this custom module installed in
That's
the
right.
OS image of every compute server so that it could access the local
Every single
repository.
client. That's right.
Yeah.
That's right. And they made themselves a huge mess because then those have to be compatible to the different versions of Lustre. And so the DOE labs, for example, had to find ways to not only have a kernel module, but to build those that are compatible across generations. And it ends up being a maintenance nightmare. At the end of the day, because NFS is standards based and adheres strictly to things like reverse compatibility, et cetera, you don't run into those same kind of problems.
Mhm.
Yeah, so it really is a new world, and especially once you can achieve these incredibly high performance levels without having to go to these custom kernel modules and proprietary systems.
You're leveling the playing field basically and opening this up in a standards-based way to allow future innovation to build on top of that,
Right.
right, David?
That's right. And by the way, I should give credit. Like the DOE labs pushed for this some 15 plus years ago, and the industry attempted to, but that attempt failed because there wasn't a commercial demand driver. AI hadn't arrived, and
Mm.
HPC was still a niche. Moreover, the NAS vendors, the guys who owned NFS, they already had their file systems, and those are not parallel file systems, and you have to throw them out and write them all over again. Was NetApp going to throw out Waffle? Was Isilon going to throw out OneFS and start over? It takes a decade plus to harden a file system, they are company defining. To this day, NetApp is really a single product company around the waffle file system. So the reason why early attempts to bring this 3D architecture into the world of NFS and NAS, the reason that failed, there wasn't commercial demand, and the existing NAS vendor had conflicted interest. But from a technical point of view, the way that got thwarted is they successfully lobbied for it to not be a standard. Parallel NFS was going to have a family of different backends. So EMC could have their backend, NetApp could have their backend, even Panasys with their backend, the T10 OSD stuff. And that is basically no standard at all when you end up having it be open, right? Okay, so that was one of the ways that their conflicted interests actually kind of thwarted things in the standards body, not to mention design by committee and the other challenges. But I'll tell you, technically, the reason why 15 years ago there was no chance of actually having parallelization of NFS actually work. And it's because we were still worried about Windows and ESX and Solaris and AIX and HPUX and BSDs and this little thing called Linux. And think about it. This very sophisticated client that now can work with a three-party relationship instead of just a simple two-way thing was going to have to go into every single one of those kernels. They are not compatible in their licensing, and they are not compatible in their virtual file system layer, the file system layer. It's the most intimate part of the operating system. So people were going to have to rewrite and make completely bug compatible, because something this complex is going to have bugs that you have to work around. And just like with web browsers and the whole battle with web browsers, it was bug compatibility that determined it. Imagine trying to make bug compatible clients across all of these different OSs. So I'll tell you what the game changer is that with AI, we've consolidated around Linux. Linux consolidated the HPC space. Linux consolidated the hyperscale space. And now Linux has consolidated the AI space. And it's that consolidation that makes it possible for us to actually build this more sophisticated parallel NFS.
Yeah, that is so cool. That's such a good history lesson too, and a lesson in standards and in the fact that for-profit companies have proprietary technologies, backends, and it takes time to build these things. Well, folks, don't touch that. I'll be right back. You're listening to DM Radio. On DM Radio, again, talking with some of the smartest people in the industry, David Flynn of Hammerspace and Mark Madsen of Third Nature. And, Mark, when I first started hearing about these guys, I thought to myself, this isn't the first time in the fairly recent past I've heard about a file system saving all the world's problems because of something called HDFS, the Hadoop distributed file system, which took the world by storm. And of course, a company called Cloudera was going to solve all the world's problems with something called MapReduce. And that didn't work out so well. But now what we're talking about here is really impressive. And David, I'll throw it over to you. This IO 500, I mean, what you basically did is you took a standard car off the lot and you raced against race cars and you came
Mm-hmm.
right in there and beat them in certain aspects, right? Because that's what it's all about.
That's right.
And that was actually the promise. I remember this with HDFS. The promise was, oh, you can use commodity servers. That's what they said. Now, in our lab, we did a tech lab about 10 years ago, and I had a data scientist come in. He actually stood up a Hadoop cluster from the command line just to see what it looked like and how it all operated. And you know what we learned
Mm-hmm.
is that the better hardware performed a lot better. If you use really crappy
Yeah.
hardware, you'd have all kind of problems. But what
Mm-hmm.
you're
Mm-hmm.
doing here with Hammerspace and with all the work in NFS and in the Linux kernel is, again, you're standardizing these things. And the beauty of a standard is that people can then integrate with it and interoperate with it. So you're opening the door
And
to
bring their own
innovation.
hardware. Bring their own hardware. And something to point out is these IO 500 numbers. This was the 10 node challenge, which meant 10 client nodes. You could build as much storage infrastructure as you want, but you had 10 client nodes, which actually meant it was very dependent on the horsepower of those 10 client nodes. And we came to the table with off-the-shelf x86 servers. It wasn't really exotic. If you look at those guys that got higher scores, it's because they had exotic client nodes or massive amounts of storage infrastructure. The thing that made ours very unique was those client nodes were the storage. We were using tier 0 NVMe shared across the compute tier. which, by the way, means it's unprecedented, the cost efficiency, the power efficiency, the space efficiency, because who doesn't have NVMe already in their GPU servers, for example, right? And this is using that otherwise stranded capacity and wasted space of server local uh, for it. And we did all if we had access to some of these super high horsepower machines, then the numbers would have excelled even more. And let me loop this back and just say that the reason this is possible is because this is native to the Linux kernel. So, for example, the data, it can be an NFS server, a participant in the parallel file system serving data, as well as a client to it. And when it finds that it is a client to itself, the same physical host is both serving and consuming the data. We have pushed upstream in the 612 kernel the local I/O change set, which allows the NFS client and server to automatically recognize each other and go, hey, we're in the same kernel. Why are we going through the formality of going over a serialized network protocol? Let's just hand pointers to memory buffers and go direct. And that allows us to get the full performance of local NVMe. So this is a true forward tier. Call it tier 0 because it's faster than tier 1, right? This isn't hyper-converged. This isn't hyper-converged or converged storage. That's just where you put a big fat software stack and you still have your custom client stack and you have, compatibility issues now compounded twice over. This is where you just use the built-in NFS server in Linux, the built-in NFS client in Linux, and those have been coded to recognize each other and short circuit, which you cannot do unless it's standard space and native to Linux. Which basically what I'm saying is not only has parallel NFS allowed NFS to catch up to these race car exotic file systems with a three-dimensional architecture instead of two-dimensional, but it allows us to take it a step further and actually move data forward into the compute and short circuit and get the whole network protocol out of the path. And by the way, it doesn't end there. It's going to go two more steps forward to where, for example, once the data is in the local SSD, GPUs are now being enhanced to know how to go and fetch the data directly from the NVMe and not have to wait on the host, but they can drive I/O accesses. This is absolutely needed for massive scale inference because you have this huge concentration of compute in the form of a GPU, and it needs access to massive amounts of data, more than can fit in memory. So the memory guys, Samsung, SK, others have spent billions of dollars and are building SSDs that are going to be capable of hundreds of millions of IOPS. This goes to the work that NVIDIA is doing with SCADA to have GPUs directly access them, and what AMD is calling Infinistore. So data moving forward in an NFS namespace into the compute tier, and then once it's in the compute tier, GPUs being able to access it directly, that's the next step. And then the step after that is to have data get put into CXL shared memory. So now across node, you have a pool of memory. And with NFS, you can promote, with parallel NFS and orchestration, you can promote the data into that shared memory device and hand out page mappings. So now your CPU with load store instructions can be talking to the contents of files. You're also not going to do that with these other exotic file systems because this has to be native in the Linux kernel. So whether it's the PHY-map interface to hand out block mapping so GPUs can access it, whether it's the DAX direct access so that you can hand out memory pages so that the CPU can directly access it, this tier 0 technology is a total game changer. And it's all made possible by, for the first time, having a three-dimensional architecture in something that's standard and built into Linux.
Yeah, I'm reminded of something I learned a long, long time ago, almost 50 years ago, by a guy named Carl Sagan. I'm sure you remember Carl Sagan, billions of stars and billions, and he would talk about like that. And he gave an example. I'll never forget this. I was watching on public television when I was like, I don't know, 8 or 9 years old. He said, imagine you're in a two-dimensional world, and he had like those squares and circles, and you can't see past things. But all of a sudden, if someone comes up and picks one of these guys up, now you're in a third dimension, and you can see
Hmm.
down. So you can see, like for a labyrinth, for example, when you're inside a labyrinth, it's hard because it's very confusing. But if you can get up outside of that labyrinth and look down, now you go, oh, turn left, right, and now you're out. Same kind of
That's
thing
right.
here.
You
You've
can route
abstracted,
things.
right?
Hmm.
You've abstracted out, and now you can do this intelligent routing. And again,
Hmm.
because you spent so many years, someone told me the number of kernel improvements that the Hammerspace team has put forward. It's in the thousands, if I'm not
Oh yeah.
mistaken, right?
Oh yeah. Yeah. The NFS 4.2 spec came from the team here, implementation in Linux, and we continue not just this local I/O patch set, but I'll tell you something else that's going upstream in the next merge window, which in and of itself is a game changer, is the NFSD Direct and NFS Direct. This is basically teaching the NFS client and server how to move data zero copy so that the CPU doesn't have to touch the data. That allows data to come from NVMe and get put on the wire without the CPU touching it and having a file system wrapped around it. So serving file system, higher level semantics without having to touch the data. To put that in perspective, NVMe over Fabrics does this for block storage. It allows block data to come from NVMe and get on the network in a block protocol. But it needs to be an RDMA network, and it's at the low level of block. We're saying here we can move data from NVMe out the network at the higher semantic level of file, and we can do it over TCP/IP networks. Doesn't have to be RDMA, and still be zero copy. And that means that you can serve data without the CPU destroying its cache by having to wade through large volumes of data. And that allows us, for example, in that tier zero scenario, for nodes to serve each other peer to peer without the noisy neighbor problem. One node can serve data to another without the CPU having to touch it. So now you can get that high performance peer to peer. And this, by the way, is a game changer for the cloud because clouds need economies of scale. They have to be large. And large networks are deep networks, and deep networks are slow networks. So slow networking is kind of a fact of life in the cloud because you have to route through a lot of switches to get from any one point to the other. But typically, when you allocate nodes to work together, they're on the same local segment. They're allocated in the same rack or nearby or whatnot. So tier zero allows the data to be orchestrated forward into the compute tier, where that local I/O can allow direct NVMe access if it's the exact same node. But even if it's a peer node, then this NFS and NFSD direct allow the data to be transmitted to each other without noisy neighbors causing CPU load and latency and so forth. So these are all game changers that are made possible by actually having something work with the Linux kernel instead of being a foreign overlay.
Hmm. And a couple quick things. And folks, look on my YouTube channel, Inside Analysis and DM Radio. We did a show earlier this year, I guess, Get Me to the GPU on Time, where we talked about some of this stuff. Because the work that Hammerspace has done has taken the number of hops that data must take to get into the GPU from an average of 10 in most environments down to 4. Well, if you're training a model with billions of parameters, I can tell you that saving 6 jumps for every piece of data is hugely important in terms of efficiency, in terms of power usage. And it's the CPUs that heat up the most, right? So all that heat that has to be cooled, a lot of that is coming from the CPU. So there are all of these sort of downstream effects, if you will, from taking this very lean approach and building things into the Linux kernel and focusing on standards-based innovation, right, David?
That's exactly right. And it's the principle of disintermediating inner layers. And when you go three-dimensional and pull the control plane out, the metadata and the router, When you pull that out, it allows the data path to be collapsed to be shorter or even coincident, where it's the same node. So you have to move to that three-party relationship so that you can shrink the data path and actually collapse it potentially all the way to where it's the same node, and then maybe put it in shared memory or put it in a device that the GPU can directly access. And then you further reduce the hops. But it basically decouples the two. So now the data is free to migrate both forward and back, because we can also demote data and stick it all the way in object storage or put it in a totally different data center, right? So the orchestration and the cheap deep capacity tier is also enabled by having separated the control plane.
And the single namespace is key because it allows for the user to get data wherever. The user may not know where that data is, and it doesn't really matter. All they care about is they access a certain window, they find the file they want. I mean, that's the
That's right.
value again of pulling the metadata management out of the data
Mhm.
path, right?
That's right. And now the metadata management is just everything any IT administrator already knows how to do. It's just NFS. So that's the beauty is from the administrator's perspective, he's still just running an NFS environment. What he's not having to worry about, know or care is the fact that under the covers, it's actually routing to many different data stores of lots of different types, and all of that's happening from behind the curtain of the file system namespace. And the movement of data is happening behind the curtain of the file system namespace. So it's really, quite incredible that you can get these boundary pushing new unprecedented levels of performance and have the extreme agility of having data capable of transparently moving across data centers, across tiers of storage, all the way from cheap and deep object storage in the cloud through and into NVMe on the GPU server, where the GPU can access it directly, or potentially even into shared memory devices on the client, where many clients can access it in parallel from shared memory.
Yeah, and that's the other thing about parallel file systems, right? Is that you can access a file while it's also being moved somewhere else, right? So this whole
That's right.
problem of locking kind of goes out the window, right?
Well, yeah, that was another artifact of the two-dimensional two-party relationship is you couldn't move things around because you were left with the legacy connection to that one party. So even if you moved it, you were still having to go through the original thing. Here, because you're connecting to the control plane and he's continually giving you different routing information to different places, moving it around is easy. It's just the control plane remains the constant, and it gives you the destination information to get to other things. And that's how we can, for example, promote the data from another data center in object storage to the same data center and all the way up into the GPU server's NVMe that's local. And it's still the same logical data because you're talking to this three-dimensional relationship. Mhm.
Yeah. Yeah. I mean, this is just fascinating stuff. We got one more segment coming up here, folks, but this is just really exciting. Like I say, we've got a couple shows with Hammerspace on our YouTube channel. Go there to check those out because what I love is the simplification for the user and for even if the user is AI, for example, because you have to grease the tracks to get that stuff into the GPUs to train the models to do your inference, for example, because you're not getting value until you do the inference. You don't get value from training a model. You get value from the inference side, and that's where the business value accrues. But we'll be right back. You're listening to
Yeah.
DM Radio. All right, folks, back here on a fascinating DM radio with David Flynn of Hammerspace and Mark Madsen of Third Nature. In like Flynn, baby, I've had that expression in my head for a long, long time. And you are in the AI platform world. And, I want to talk about this AI bubble that everyone keeps clamoring about. And the bottom line is, and you were just saying this a moment ago on the break, we have got to be able to monetize AI in order to avoid a bubble. If you're just building capacity all day long and there's no one making money from that, well, that's when you are over your skis, as you suggested, and we've got a real problem. So
Yep.
inference is the key. You train the model, but then you have to do inference to get the business value. That's where the monetization comes from, right, David?
That's right, right. The inference and the challenge there is that with training, sure, they're large data sets, but it's the same data set over and over again. With inference, it's new data all the time, which means we have to go and get that data. So data fragmentation becomes a real concern. Data conditioning, vectorization of it, making it accessible through RAG, et cetera. And this is what AI data platforms are there to do is to challenge it. Because I'd say that training is compute in heavy and relatively data light because it's the same data set, whereas inference is lighter on compute, but much heavier on the data, and the data logistics side of things become much more the pain point, overcoming the data fragmentation, the preconditioning needs, and so forth.
Yeah, well, I mean, one of the things we've said on the show, and I'll throw it over to Mark here, is that if you want to get your organization AI ready, one thing you really need to do is get your data house in order. And, talk about something
Mhm.
that had no commercial driver for years. What is it, like 7 copies of data is the average in most environments? And it's like, where is all that stuff? You have all these closets everywhere filled with data, and there was never any way to get a strategic view across all those different file systems, but that, of course, is what Hammerspace
and
sought to solve, right?
and it was unstructured data that we thought was not that usable. It was,
Right.
structured data was where all the value is. But now with AI, and we can actually machines can actually understand what's in the unstructured data. Suddenly, all of that has become super useful. So yeah, this is really, I would say, the key challenge right now with having AI be monetizable and not just be a bubble and pop and cause a whole bunch of, because this is compounded by the fact that the infrastructure players, especially the storage infrastructure guys, they're going, hey, this is a new excuse to ask you to totally do a forklift and replace all of your storage with new storage that's faster, and et cetera.
Right.
And that's and you know what that's led to? Flash is on allocation. Hard drives are on allocation through 2027 because
Wow.
people have been willing to pay that to do greenfield forklift upgrades. And but yet that still doesn't solve the problem of how to go and collect all of that existing data from the different fractured things, because now you're just basically saying I have to do a data migration to get it there. That won't work. So there's two reasons why it won't work. Number one, we can't afford to do forklifts just from the whatever. So being told, oh, you need to deploy this new storage. And number two, even if you did the forklift, now you just have even more silos that you got to move data between. So moving to a three-dimensional world with data that's orchestrated behind a single namespace allows you to take your existing storage and make it, accelerate it, virtualize the data in it so that it becomes AI capable environment. Maybe you augment it with some moderate amount of flash based storage, which, by the way, can be the flash in the compute tier with tier zero, so that you don't have to deploy any new shared storage. Between tier zero and the ability to incorporate, because it's standard space, we can use your existing NAS, we can use your existing block file and object storage. And here's the magic, it makes it faster, even on just a single system like an Isilon. We've had customers who have done very extensive testing that have shown that it makes it 2x to even 10x faster to use this three-dimensional architecture on front of Isilon, because Isilon, it was a flat 2D thing, which had a bunch of gateway nodes. Those are the intersections that route data to the backend storage. That's why they have this internal InfiniBand or fabric like VAST, right? But that creates this huge congestion. Once you move the control plane out, now the data can be routed coherently so that you're going to different nodes for different things, and it gives it a perfectly sorted access pattern. And that's how you can amplify the output of the existing infrastructure. So we're saying, come to the table with your existing infrastructure. We'll accelerate it. We'll orchestrate the data across it, put it behind a single namespace, and do the preconditioning, vectorize it, put it into RAG. And this is what the AI data platform does. Assimilates data from existing sources, incorporates and virtualizes them behind a single namespace, and allows these preconditioning steps so that you can use it for RAG.
Well, and rip and replace is always brutal. We did a show a couple of years ago on DM radio called something like "Sunsetting Applications and Other Fairy Tales from the Enterprise." It's just a very difficult thing to do, and so to come in and have an overlay on that, I'll throw it over to Mark just to comment on. We got about 5 minutes left in this segment. That I think it allows organizations to sigh a bit of relief because they know they don't have to rip this stuff out. If you can have an overlay that sees into these things and focus on the data that matters and orchestrate the data that's generating value, I think that's one of the keys to success. But Mark, what do you think?
Yeah, I think it is, and it's kind of a replay, like you said, of things that happened, with the database market and the storage area networks. Was every server ran a database. We had 50 Oracle databases. We got 50 Oracle servers with 50 piles of disk. And then people said, well, maybe we could consolidate that storage on the network and we could have storage servers, and thus we get companies like EMC rise. And now it's 50 servers with the code talking to one big pile of storage, which has its strengths and weaknesses, and occasionally you still had a special beast in the corner, but that was the rarity. And like David was saying, with content storage, whether it's files of text or images or audio, well, actually, in that example, you probably had three different things, each storing those types of data separately. And you throw it into a big corporation full of documents, and you had content management systems which may be standalone, or content management system backed by a network storage appliance, right? So you have some NAS sitting in the corner serving three different content management systems, and it's just a mess. And that's the mess that now needs to be cleaned up at a storage layer, which is different. And I think, that's where the interesting convergences are going to happen. But, we already learned that bring in EMC and just throw 50 of these on there. Well, that was a 3-year project that cost us millions and millions of dollars. And it's better if you can leave things in place and slowly integrate them over time by having something sit in between those. But
That's right.
that's more than just the protocols or like the NFS piece, right? So what I'm kind of interested in where what
Mm.
David's response to that is,
So,
because once we've solved the protocol or the
well,
standards layer, now we have to talk about, okay, how do I orchestrate, right? Because there's
that's exactly
integration
right.
and then there's orchestration. So let's talk about
So
that.
yeah, well,
Curious.
and that's actually what Hammerspace has spent all this time on because there are now the major existing storage companies talking about incorporating parallel NFS. Um, Pure has started talking about it. Dell with Project Lightning. Everybody needs to move to this three-dimensional architecture and NFS. Even VAST is going to have to do that and move away from their shared everything NVMe over fabrics two-layer architecture to one that's routed instead of proxy. You watch, they're going to have to do that. But that's just to get to a high performance file. The thing is, that's just the starting gate because the next thing you do with that 3D architecture is you make it possible to move data, to orchestrate it. You make it possible to incorporate existing data sets by reference instantly. That's data assimilation. So, data assimilation, data orchestration. And once you have the control plane separate, now you can do asynchronous, eventually consistent replication across data center and do active global namespace. And so this is where, and then the next step to that is have it automatically be processed through vectorization and put into a RAG system so that it can be referenced for inference, right? And that's what AI data platform is. So while everybody else is still working to catch up on step number one, which was to introduce parallel NFS, there's steps 2, 3, 4, 5, 6 after that with what it means to truly virtualize in place data. And the challenge is the storage vendors, they have a conflicted interest. They don't want to virtualize in place data. They want to give people an excuse to upgrade their storage and to
Hmm.
sell more storage. So they're simply conflicted. Vast isn't going to do this because they would be undercutting their business. The same with NFS, with NetApp and Dell. Anybody who's in the business of selling storage infrastructure isn't going to want to sell a virtualization acceleration layer that lets you use your existing storage.
Wow. Well, folks, let's just
Yeah.
jump right into the podcast bonus segment here. We got about 7 more minutes. And I'm just fascinated by the vision that you've got here. And I'm reminded of a couple things. You actually said something to me. I don't think it was on a show. I think it was just at a break maybe 8 or 10 months ago that I have not stopped thinking about. It was very interesting. You said something like, if we had this kind of technology, the three-dimensional architecture you're talking about, the Anvil, which is how Hammerspace refers to the metadata management component. You said if we had this 20 years ago, we wouldn't have had to dumb everything down for the cloud. And I thought to myself, wow, because you think about all these APIs. Well, what is an API? It's a toll booth. An API is a toll booth, and you have to pay the toll to get the data out of the API or whatever. And all this movement of stuff into the cloud, it's like, all right, now the cloud is a big silo, basically. And you have your on-prem and hybrid cloud. It was became a nightmare. But do you remember saying that? Because I thought that was
Yeah, yeah.
really fascinating.
Well, the way I like to say it is the cloud isn't what we were promised of run anything, anywhere, utility computing, so forth. And it's not because data has been stuck on flat Earth, two-dimensional. Data migrations, hybrid cloud, nearly impossible. We needed the three-dimensional architecture so that data can move freely. Because once data becomes orchestrated, now you can compute anywhere, especially if you're actually making it faster.
Wow.
So we can deliver on the promise of run anything anywhere, even the most data intensive applications, once data becomes orchestrated. Because otherwise, we live in the world of mainframe redux. We live in the mainframe era again. You choose which vendor. Is it a PDP? Is it an IBM? Who's the mainframe? And by the way, which of their mainframes? Is it US East? Is it US West? Because once you put your data there, that's where all your computing has to happen because of data gravity. The thing about this three-dimensional architecture and data orchestration, assimilation, global namespace, this virtualizing and accelerating data, is it allows us to have the cloud we were promised, a cloud where you can run anything anywhere and even run AI workloads with our most performance demanding data intensive.
Yeah.
Because, and I'll leave the one last thought that AI is the forcing function that's forcing the industry to finally wrestle to ground our demons. And those demons are data gravity, data fragmentation, and those challenges that the storage vendors and the infrastructure vendors have exploited for years using their customers' own data gravity against them
Mm.
as a way to keep them trapped on infrastructure.
Yeah, I remember referring to a lot of these cloud environments with their egress costs as Hotel California. You can check out anytime you like, but you can never leave, right?
That's
It's too
right.
expensive. I mean, it's too expensive, and you're trapped, right? It's
You're
basically a
welcome to compute
vendor-locked.
anywhere, but if you want to do it near your data, you're going to have to do your computing here. So you're welcome to check out. You just can't run it there.
That's pretty funny. I've got about 2 minutes left. Closing thoughts from Mark Madsen. What do you think?
Yeah, I mean, there's a lot still to be done, right? That's kind of where I come back to. But yeah, I've been frustrated with cloud as the mainframe for a long time, and I've also seen the inside of the sausage making factory in cloud, and earlier David mentioned having to be bug compatible because you have this kernel module that's doing something and it's got to work exactly the way everything else works and reproduce those bugs because people expect them. And the cloud is exactly the same way, except you don't know what the bugs are. Um, I know for a fact that there are storage protocol errors in two of the clouds because we're involved in fixing one of the cloud storage protocols, but they had had silent data corruption for 4 years. But it was such a rare, infrequent thing that one customer in one region might experience it once every 2 years. But you amplify that by a million customers, and there are people being affected. And it's not until you have a single workload for one customer driving enough traffic, whether that's I/O, file accesses, data reuse, whatever, that it becomes visible to them once a month.
Hmm.
And then suddenly it becomes a problem and it gets fixed. And David talking about the forcing function, to me, that's what we're going to start seeing here now with some other stuff. It's here's a forcing function that starts to raise the visibility of various problems. I mean, not storage protocol bugs like we were debugging, but other things. And raises the visibility of oh, all your legal documents are in New York, but all of your AI smart guys doing some interesting project to, robo sue people is happening in California. And how do I get one to the other? Because I've got infrastructure in two places, but it's split. And now
And we
it's,
haven't even talked about how you govern and secure that,
oh,
which
absolutely.
if
Yeah.
you're copying things around is a complete farce, right? If it's orchestrated, you at least have a way to
Yeah.
rationalize because it's all stays
Right.
behind the curtain.
Wow.
Yes, that's exactly it.
Well, folks, what a fantastic conversation. I'm sure we'll be talking to these gents again in the future. Look them up online. David Flynn, Hammerspace, Mark Madsen, Third Nature. Send me an email if you want to be in the show, info@dmradio.biz. It comes right to me. We'll talk to you next time. You've been listening to DM Radio.